An ancient geometry problem falls to new mathematical techniques. Please check the link in description. It will change your life. It is the best way of supporting this channel. Around 450 BCE, Anaxagoras of Clazomenae had some time to think. The Greek mathematician was imprisoned for claiming the sun was not a god, but rather an incandescent rock as big as the Peloponnese Peninsula. A philosopher who believed that reason rules the world, he used his incarceration to grapple with a now famous math problem known as squaring the circle. Using a compass and a straight edge, can you produce a square of equal area to a given circle? Surprisingly, mathematicians are still working on this question. And they are making headway. A paper posted online last week by Andras Maith and Oleg Pikurko of the University of Warwick and Jonathan Noel of the University of Victoria is the latest to join in this ancient tradition. The authors show how a circle can be squared by cutting it into pieces that can be visualized and possibly drawn. It's a result that builds on a rich history. The exact question posed by Anaxagoras was answered in 1882, when the German mathematician Ferdinand von Lindemann proved that squaring the circle is impossible with classical tools. He showed that pi, the area of a circle with a radius of 1, is a special kind of number classified as transcendental, a category that also includes Euler's number, e. Because a previous result had demonstrated that it's impossible to use a compass and a straight edge to construct a length equal to a transcendental number, it's also impossible to square a circle that way. That might have been the end of the story, but in 1925 Alfred Tarski revived the problem by tweaking the rules. He asked whether one could accomplish the task by chopping a circle into a finite number of pieces that could be moved within a plane and reassembled into a square of equal area, an approach known as equidecomposition. Put another way, two objects are equidecomposable if they can be broken up into pieces of identical size and shape, or, more precisely, if you can split them into finitely many parts such that the corresponding parts are congruent to each other, Pikurko said. A 1964 paper was the first to make substantial headway on Tarski's version of the problem. The authors showed that the equidecomposition could not be done with scissors. The task, if it was possible, would require more complicated fractal pieces, riddled with holes and intricately jagged edges. That's where things stood until 1990, when Miklos Lachkovich answered Tarski's question with a resounding yes, a circle could be reconfigured into a square. To visualize Lachkovich's achievement, imagine a circle and square side by side on a page. He demonstrated that if the circle was partitioned into at most 1050 pieces, all of them complicated and with unusual shapes, those pieces could be moved over, without even being rotated, until they completely filled in the square. But to arrive at this result, Lachkovich didn't work with shapes. Instead, he transformed the geometry problem into a graph theory problem. He took a large graph with two separate sets of vertices, one corresponding to a circle, the other to a square, and then established one-to-one correspondences between vertices in one set and those in the other. Stan Wagon, a mathematician at Macalester College, described the results as jaw-dropping. Lachkovich showed how to take a circular space and make it straight. There was a catch, however. Lachkovich's proof is an existence proof, what mathematicians call non-constructive. He proved that it could be done, but he couldn't say how to construct the pieces, nor could he describe them in any way. Worse, the pieces are non-measurable, which means it's impossible to determine their area.